Okay, ladies and gentlemen, so at this point we should have cut out our colored circle cardstock. We're going to use that as our Ferris wheel model. We're going to eventually attach that onto our white note card with the metal brad fastener in the center of the circle, and we're going to have a Ferris wheel. But first what we want to do is go ahead and divide our circle up into 12 30-degree angles. And so there should be a center point on there. I used pencil when I made these templates. I put the little center there of the circle. What we want to do is go ahead and take your ruler and draw a diagonal, or your protractor, draw a diameter all the way through your circle to divide it in half. After drawing a diameter all the way through your circle to divide it in half, you can now use your protractor, placing the center point of your protractor at that circle. By placing the protractor in the center of your circle, you could go ahead and mark off 30-degree segment, 60 degrees, 90 degrees, 120 degrees, and so on. Our goal is to divide it up into 12 equal 30-degree segments. So you can place the center of your protractor, the bottom little center point of your protractor at the center of your circle, and mark off 30-degree segments around the circle. Connect them, and so they're 30-degree sectors. And we have 12 equal slices of pie, so to speak. Do the math jokes, Chloe. Just do the math jokes. Yeah. Okay, so after we have our 30-degree segments, right, 12 equal sectors around our circle, we want to go ahead and make sure that we have this horizontal and vertical axis, our horizontal axis PQ and vertical axis ST. We can go ahead and draw those with the ruler on the white note card. The directions on your Bellwork have you punching a hole in the center of your circle and affixing it to your note card first. However, I think it might be easier to draw with the ruler and make your axes on your white note card alone first. And so it might be easier to go ahead and draw a horizontal axis and label it PQ. And then take your protractor in the middle, make a center point, and then get 90 degrees to make it perpendicular, and draw the vertical axis ST with just the note card before taking your circle and attaching it. That might be easier to draw the straight line so you're not running into that metal fastener. Alternatively, you could follow the directions and punch the hole and attach to the circle and then draw your lines last, but I think that's going to be more difficult. And so I think we should go ahead and do the note card alone first. Draw a horizontal axis, label with your protractor 90 degrees, and a vertical axis. And then on the ends of your horizontal line segment, you could put point P and point Q. And on your vertical line segment, you can label that S and T. The center of your circle should correspond to the intersection of these line segments. That'll be like the origin, right? You'll punch a hole in your circle with the metal brad fastener. Poke that through the note card origin, and then fold the little metal fastener in the back so that you've got your Ferris wheel attached. Okay, ladies and gentlemen, so at this time most of you have your circle divided into 12 equal 30-degree sectors. You've labeled your note card with a horizontal and vertical line segment. The center intersection of those line segments is going to be the origin. We'll attach our Ferris wheel with a metal fastener to the note card so that it looks like here our digital picture. Next, along the outside of your circle on the white note card, you're going to go ahead and label. Make sure you line up carefully this initial point. You can go ahead and darken a little point. That's going to be our kind of 1, 0. So go ahead and line up the line segment on your blue Ferris wheel with the initial ray, the positive x-axis, and make kind of a dark point. So I just drew in kind of a dark point on that positive x-axis on the circle, right? A dark point right on the edge of my blue circle. Make a dark point right there. That's going to be our point A, initial point 1, 0. When that's perfectly lined up, we can go ahead and label on the note card 30-degree segments all the way around. On the white, you're going to label, but make sure you're lined up. You're lined up on that positive x-axis. So we'll label on the white note card 30 degrees, 60 degrees, 90 degrees, 120 degrees, 150 degrees, 180 degrees. You should be back at that horizontal line segment PQ. Third quadrant, 210 degrees, 240 degrees, straight down, 270 degrees, back to that vertical line segment ST. Fourth quadrant, 300 degrees, 330 degrees, and back to my horizontal line segment. You're writing these values on the white note card. Our goal is to be able to spin that initial point that you darkened on the side, spin that a given angle rotation, and stop when we line up at one of those angle measures. I'm seeing some nice Ferris wheels. Good job, you guys. Questions about the construction? It looks like you're doing a good job, and some people are different places, and that's okay. We'll have a chance to kind of catch up as we begin completing our chart. So we're going to do some of your homework problems together. What you're going to work on after our quiz, you'll have some time to work. You're going to continue completing this chart on the back of your Day 5 exact values worksheet. We're going to go ahead and use our Ferris wheel model to start this chart together. So everybody please find your Day 5 exact values worksheet. There's a chart. Everybody find it? Big chart on the back. Everybody find it? Big chart. We're going to start completing this together right now to give you a template as how you can complete your homework. And then we're going to use this completed chart next class to develop the graphs of our sine and cosine Ferris functions. Thank you, Angel. So everybody find the chart? What we're going to do is we're going to use our rulers now to measure the directed vertical distance from point A on my circle, right, back to PQ, my horizontal line segment, after a given rotation of theta degrees. We're going to use our ruler to measure the directed horizontal distance from my ending terminal point A back to the vertical line ST. We're going to label those in our columns, and then we're going to use our calculators, just like in our activity, to get the calculated distance that should be based on right triangle SOHCAHTOA trigonometry. Let me show you what I mean. So what we're going to do is just in a large chart for me to write in. It's the same as your chart, it's just more space for me to write in. We're going to go ahead and take our ruler, and we're going to spin, right? We're going to spin our point A a given angle rotation. In the first case, we're going to leave it be. We're going to leave our point A right there at 1, 0. If we take our ruler and measure the directed, right, the directed vertical distance of point A above line PQ, we get 0, right? This point hasn't been rotated at all off of this horizontal line segment, so its distance above or below is 0 centimeters. However, it is, right, 5 centimeters away from that vertical line, ST. It's 5 centimeters away from the origin. So my measured distance from point A to line ST after a rotation of 0 degrees is 5 centimeters. In our chart, we can fill in our measured distance in the first column after a rotation of 0 degrees is 0 centimeters. Our measured distance of point A back to the vertical line ST is 5 centimeters. That's our third column, bless you. We can fill that in our first row. Next comes the calculated vertical distance versus the calculated horizontal distance. That's columns 2 and 4. Let's take a look at that. So we know that this, after a rotation of theta degrees, a right triangle can be formed just like in your activity by dropping down this vertical leg length and connecting back to the origin, the horizontal leg length, and labeling them x for horizontal and y for vertical. We know a trig ratio can be written with my angle. Cosine of an angle is a fraction. Cosine of theta equals adjacent over hypotenuse, so that would equal x over 5. And solving for x, I would get 5 times cosine theta. Similarly, my vertical displacement, y, also appears in a trig function. What ratio is the sine of theta? Well, the sine of theta would be opposite over hypotenuse. That would equal y over 5. Solving for y through multiplication would get y alone. My y coordinate would be 5 times sine of theta. Everybody, let's write this in our top of our column. To get the calculated distance, we're going to use 5 times sine of theta to get my vertical distance. My last column, we're going to do 5 times cosine of theta on the calculator to get my horizontal displacement from the origin. In this way, we could do 5 times sine of 0 degrees on our calculator and get 0. And 5 times cosine of 0 degrees in our calculator and get 5. Everyone, at this time, we should have our first row complete in your chart. Everybody have your first row in your chart complete? Yay! Let's take a look at our second one. Next, we're going to rotate. Everybody take your Ferris wheel. That initial point that's dark on the perimeter of your circle, you're going to spin that until it lines up with 30 degrees. You know you're lined up when your next 30-degree line segment makes a straight line with your axis. Everybody lined up, 30 degrees. You're going to take your ruler. You're going to measure this vertical displacement above the horizontal line. You're going to measure this vertical displacement using your ruler in centimeters. I'm measuring in centimeters. I'm getting about 2.5. I'm getting about 2.5. So with my vertical measurement, I'm getting about 2.5 centimeters. Then I'll go and do my horizontal. My horizontal is back to the vertical line ST, so I'm holding it this way. I'm holding my ruler this way, and it looks to me like I'm getting about 4.3, except I'm doing it up here. I'm doing it up here. I can see it better up here. So I'm getting about 4.3. Are you guys getting that? I'm trying to do point A back to that vertical line segment. Yeah, I'm getting 4.3 again. So our chart now has 2.5 for 30 degrees vertical displacement and 4.3 centimeters for column 3 measured horizontal displacement. Now let's calculate in your calculator, everybody, 5 times sine of 30 degrees. So in your calculator, do 5 times sine of 30 degrees. So in my calculator, 5 times sine of 30 degrees, we're getting 2.5. And in my calculator, 5 times cosine of 30 degrees, 5 times cosine of 30 degrees, we're getting 4.3301. Guess what? Bless you. We can now complete our row 2. So we've got 2.5 centimeters measured, 2.5 is what my calculator gave me. 4.3 is what I estimated measuring. 4.330 is what my calculator gave me. We got it? Row 2. Let's do 2 more. Now we're going to skip ahead. Let's go all the way to 150. So take your initial point, 1, 0, and we're going to spin it 150 degrees. Where are we going? Still spinning, just keep spinning, like Dory meets the unit circle, all the way to 150, quadrant 2. Everybody, so your initial point A now is in quadrant 2. Everybody see it? 150 degrees. Take your ruler. We're going to measure the vertical displacement. When I do that, I get about 2.5. We're going to measure the directed horizontal displacement. I'm getting about 4.3 again. Five times sine of 150 in my calculator. Five times cosine of 150 in my calculator. Uh-oh. We got a problem. Houston, we have a problem. I don't have Houston Witchoff in my class anymore, but it was way more funny when I did it, Christy. Hello. Houston, we have a problem. I got negative when I did 5 cosine of 150. I got negative 4.33. Did I measure that? No, I got positive 4.33. What's going on here? What's going on with this negative business? Did we make a mistake, Rachel?
It's on the other side of the x-axis, and x is the sine.
Absolutely. It's on the other side of the y-axis, this vertical line segment ST. So my x-coordinates in quadrant 2 over there are negative. If you told your friend a road map to get to that point A, you'd say left for your x-coordinate. It would be negative and then up, your positive y-coordinate. And so this is not a mistake. Our calculator is telling us the calculated horizontal displacement is negative because we're to the left of the origin. We measured 4.3 because distance size positive, but negative is what we should get for our value. And that makes sense because we're in quadrant 2. Good job. Thank you, Rachel. 1 to go, and then you guys will have it. So we spun finally to 270 degrees. So let's spin all the way to 270. And now we're back on that vertical line segment, ST. Is everybody back on ST? After a rotation of 270 degrees, my measured horizontal vertical displacement is straight up 5. I'm back to a 5. It's just that I'm below the origin. My calculated vertical displacement in my calculator by doing 5 times sine of 270 is telling me that I'm below, because I'm getting a negative 5. Everybody see that? So I'm measuring positive values, but we're recognizing what's going on here with my negative depending upon the placement of the terminal side of the angle's ray. We're 0 centimeters to the left or right of the origin. Our calculated horizontal displacement is also 0. We're verifying that with 5 times cosine of 270 degrees equals 0. You guys, we are 3 rows down. Yeah! Look at that. So at this stage, we've got our 0, our 30 degrees, 150, 270. We've tried to give you, right, a positioning in a couple different quadrants here, right, so that you have a template to complete this. This is part of your homework assignment, and we already did 4 rows for you. So we've got a good start using our Ferris wheel. So measured distance are found using our Ferris wheel and the ruler. You're going to work on this after your quiz. You can do this first, okay? Don't do the front side. Do this first while you still have access to the ruler and stuff. And make sure you return, right? Make sure you return the ruler at the end of the class, but you can use it for your quiz if you want to as well. For a couple pictures that you need to draw anyhow. All right. What questions do you guys have about our Ferris wheel in the chart? Are you guys okay? Awesome. Then I'm going to go ahead and pause the recording now, and we'll do our homework check. Ladies and gentlemen, today we're going to have a mini lesson where we determine exact values of sine and cosine using what we'll call reference angles. It's going to give us a connection between an angle of any rotation, positive or negative, and acute angles that we already know about with our sine and cosine SOHCAHTOA ratios. So our first content objective is going to be find exact values of trig functions using special triangles and what we call a reference angle. The second objective we've already addressed, and you're going to have a chance to continue using your Ferris wheel to model the sine and cosine functions as directed displacement from the origin, either right or left using the cosine function, up or down the y-coordinate using the sine function. So we've already taken care of the second one, which means that after our mini lesson with reference angles, we'll have a chance to do a little review before your quiz, and we'll be taking your quiz second half. To that end, let's go ahead and get cracking. So, recall from last class's Bellwork, we went ahead and filled in the missing side lengths and angles for our special 30, 60, 90 triangle back from geometry. Recall the ratios for sine, cosine, and tangent. I know that sine is simply the ratio of opposite side length to hypotenuse length. So be ready. Let's get warmed up for our reference angles today. Sine of 30 degrees, go ahead and tell the class the ratio when I call on you. So what would be the sine of 30 degrees? Everybody find it? So sine of 30 degrees would be, Caitlin?
1 over 2.
Absolutely. Opposite over hypotenuse. Perfect. Everybody find cosine of 30 degrees. Everybody find it. Get ready. Look at your triangle. Get ready. Joe.
Square root of 3 over 2.
Absolutely. Square root of 3 over 2. Tangent of 30 degrees. Opposite over hypotenuse. That would be 1 over root 3. After rationalizing the denominator, however, you'll typically see that as root 3 over 3. Sine of 60 degrees. Everybody find it. Get ready. Sine of 60 degrees. Taylor.
The square root of 3 over 2.
Good, thank you. Sine of 60 degrees is square root of 3 over 2. Cosine of 60 degrees. Get ready. Go.
1 over 2.
Good. 1 over 2. And then the tangent of 60 degrees, that's opposite over Jason. This time root 3 over 1 is just going to reduce to square root of 3, and that's how it's taken. So what we're going to do is use the fact that these special angles, 30 degrees, 60 degrees, and also the 45, 45, 90 special triangle from geometry, are going to give us exact values on the unit circle for our special 16 points along the perimeter, no matter where the terminal side lies, quadrant 1, 2, 3, or 4. We just have to find a reference angle that matches. So we're going to be using your green sheet today on your exact values worksheet, your homework worksheet. You're going to use the green sheet, not your calculator, in order to get these exact values. So let's go ahead and first introduce a new term, and that's called a reference angle. A reference angle is the measure of the acute angle that connects the terminal side of a given angle to the nearest x-axis. Depending where we end, we'll be going either forward or backwards, but we're always connecting the acute angle to the nearest x-axis. Consider a rotation of 135 degrees. Where's the nearest x-axis? Well, in this case, the nearest x-axis is right here at 180 degrees. So, a reference angle would measure the acute angle in between the terminal side of your given angle, 135 degrees, and the nearest x-axis, 180 degrees. Guess what? My reference angle in this case would just be 180 minus 135 is 45 degrees. It's that easy. It's the measure of the acute angle that connects the terminal side of your given angle to the nearest x-axis. Take a look at 210. 210 degrees. We're spinning, we're spinning, we're spinning. Stop. Where's the nearest x-axis? Well, again, the nearest x-axis is 180 degrees. So the reference angle in this case is the magnitude of the acute angle, always positive, that connects 210 degrees back to 180 degrees. To get that, I can again do a subtraction, big minus little. 210 minus 180 is 30. So my reference angle in this case for 210 degrees is just 30 degrees. Who cares? Because my special triangles, 30, 60, 90, and 45, 45, 90, have ratios, right, for me for sine, cosine, and tangent. Those are going to correspond exactly to the trig values for an angle rotation that's obtuse, like 135 or 210. All I need to do is figure out the reference angle that it corresponds to, and it'll have the same exact trig values for sine and cosine and tangent. The only difference is we might have positive versus negative. Let's go ahead and take a look at a couple more reference angle practice, and then we'll do exact values, and then we'll be good to go. So 240 degrees. Everybody find the nearest x-axis. The nearest x-axis, again, is 180 degrees. Therefore, my reference angle is big 240 minus little 180 is a reference angle whose magnitude is 60 degrees. The sine of 240 degrees is going to be the same as the sine of 60 degrees, unless I need to add a negative based on the quadrant in which the terminal side lies. Lastly, reference angle for 330 degrees, where's the nearest x-axis? Finally, we have the nearest x-axis to 330 is 360 degrees. So we're over here this time. Remember, it's always the measure of the acute angle that connects the terminal side to the nearest x-axis. What's the magnitude of the acute angle between 360 degrees and 330 degrees? 30 degrees. Who cares? Well, because notice how all of my reference angles correspond exactly to my special triangles from geometry. I'll just do a couple that are like your homework worksheet. Let's find the cosine of 60 degrees. So the cosine of 60 degrees, that's an exact value, and that's already on my green sheet. After spinning 60 degrees, I'm in quadrant 1. Cosine values in quadrant 1 are positive, and from my green sheet, I see that the cosine of 60 degrees is already given. I don't need to change any signs. Everybody find it? What's the cosine of 60 degrees? Chrissy.
0.5.
Awesome. So my cosine of 60 degrees is 1/2. And let's use the ratios, the fractions, exact values. We won't need to use a calculator at all. Good. Sine of 135 degrees. Okay, let's spin. So 135 degrees, here we go. This time I'm ending in quadrant 2. In quadrant 2, sine values, right, are positive because y-coordinates are positive. But I look at my green sheet, and I don't see 135 degrees anywhere. Do you? No. Is this time to quit? Want a bowl field trip? No, we're going to find a reference angle. A reference angle whose values of sine and cosine are exactly the same magnitude as the sine and cosine values for 135 degrees. What's the reference angle for 135 degrees? That red acute angle, we just did that, it's 45 degrees. The sine of 135 degrees is the same as the sine of 45 degrees. What's the sine of 45 degrees, Nathan?
Square root 2 over 2.
Absolutely. So the sine of 135 degrees is the same because we use the reference angle of 45 degrees. That's it. Easy cheesy. Let's do another. 210. Just keep spinning, and here we are, 210. Reference angle for 210 is 210 minus 180 is 30. Guess what? The cosine of 210 is the same magnitude as the cosine of 30 degrees. From my green sheet, I see the cosine of 30 degrees is root 3 over 2. With one important difference. In which quadrant does the terminal side of 210 degrees lie? Quadrant 1, 2, 3, or 4? Casey?
What was the question?
In which quadrant does 210 degrees lie? 1, 2, 3, or 4? 3. Are x coordinates positive or negative in quadrant 3? Mark?
Negative.
Negative. So my cosine values, which are the x coordinates, need to be negative, so this is the only difference. You have to purposely add the negative because my terminal side of the angle lay in quadrant 3. Sine of negative 120, here we go. Spinning the opposite direction this time. Negative 120, we're spinning negative 90. Negative 120 would be right here. To get a reference angle, I must connect to the nearest x-axis. The nearest x-axis is still 180 degrees, right? But now, because we went in a negative direction, it would be negative 180 degrees. What's the difference between negative 180 degrees and negative 120 degrees? 60 degrees. My reference angle in black is 60 degrees. The sine of negative 120 degrees is the same as magnitude as the sine of 60 degrees. I know that is root 3 over 2. unless I need to add a negative. Based on the positioning of the terminal side of my given angle, do I need a negative for the sine of negative 120 degrees? Do I need a negative for that, Hans? Yes, I'm in quadrant 3. Look at that. My y-coordinates are negative here. I'm beneath the origin. I need a negative, and that's the only difference. I have to add that on my own. 1 to go, sine of 405. Let's spin. 90, 180, 270, 360, 405 is right here. 405 is co-terminal with 45 degrees. 45 degrees has sine and cosine values of root 2 over 2. Because I'm in quadrant 1, it's still positive. These exact values are going to be how you complete your homework assignment page 1, the first side. Everybody good? No book work tonight. Yeah. After the quiz, you'll work quietly on your day 5 exact values worksheet. Do your backside first with the chart to complete that. Use your rulers. And then we're going to turn everything in on the front tub so that I have the next hour. Please don't take any scissors, don't take any rulers, don't take any protractors. I need them all for my next class. All right, let's go ahead and take a look at 1, 2 review problems, and then we'll go ahead and get going on your quiz. I'm going to give you a chance right now to work on 1A and B. And number 2, these look just like your quiz questions. I'm going to pause the recording, and we're going to come together in a few minutes to check our answers. And I've shown my work too. So let's go ahead and work on. Okay, ladies and gentlemen, let's go ahead and take a look at these review questions. Some of you are still working, and that's fine, but I do want to make sure everyone has enough time to work on their quiz during the second half of the class. And so what I've done is I've gone ahead and shown in my work here, do I have an opposite side angle pair in that first triangle 1A? Yes, we do have an opposite side angle pair. 5 centimeters is opposite 40 degrees. Therefore, we can use law of sines, where we set up a ratio. X is to sine of 83 degrees, just like 5 is to sine of 40 degrees, and solve through multiplication. I'm getting about 7.72 centimeters. Raise your hand if you already had 1A. Did you get the same thing for 1A? Law of sines. Good job, you guys. If I had a right angle, I would have used regular SOHCAHTOA. It's just I didn't have a right angle. Take a look at B. Do I have an opposite side angle pair in 1B? No, I don't. Do I have enough information to do 180 minus to get it? No, I don't. And so I can't use law of sines. I can't use right triangle trig. I have to use law of cosines. And so I'll use law of cosines by setting up my formula. Remember, the opposite side angle pair drives the party. X squared, right, equals 10 squared plus 14 squared minus 2 times 10 times 14 times the cosine of 60 degrees. I'll solve by taking the square root and get about 12.49 feet. Raise your hand if you already had that. You get law of cosines in the second one? Great job, you guys. Way to go. We'll give you one form of law of sines and one form of law of cosines on your quiz. Lastly, if we do the airplane problem in a picture, we can see, right, that I have labels. I know that the altitude was 5,000 feet when it was 30,000 horizontal feet away. We can use that information to set up a right triangle trig ratio, and I used tangent. So I know that tangent, right, of my angle theta, which I can get in the party there by using alternate interior angles with parallel lines are congruent. I know that my vertical leg length here would be the altitude of the plane that was 5,000 feet. I know my horizontal feet away was the 30,000, therefore opposite over adjacent is 5,000 over 30,000. Inverse tangent solves to find the missing angle measure, and I got about 9.46 degrees. If I have a right triangle, guys, use right triangle trig. Don't use law of sines or law of cosines. If you got a right angle, use Pythagorean theorem or SOHCAHTOA. It'll be much more efficient and easier. Questions about our quick and dirty review? Okay, then it is calculator allowed, but we want everything off of your desk. Everything off your desk. I'm going to stop the recording and save it.